Here we go. So the next lesson we've got today is going to be 10.3, the next section here. It's titled Apply Properties of Chords. So before we get into anything here in this section, the first thing we need to talk about, in the title there, it says chords. We need to review that concept. So what a chord is, and if you remember from section 10.1, we defined it. What a chord is, it's going to be a segment whose endpoints are on the circle. Okay, so we need to know what a chord is. So I think we talked about a special type of chord. A diameter is a chord. Its endpoints are going to be on the circle, but it's going to go through the center. All right, so a generic chord, though, is just any segment whose endpoints are on the circle. All right, so there's a lot of different theorems that we're going to talk about today. A lot of things that we need to know about chords, special things that happen when we draw a chord in a circle. All right, so here it goes. So let's go ahead and first write down this fact here. This is the first thing you need to know. Any chord is going to divide the circle into two arcs. All right, so this can happen in a couple of different ways. So what could happen, and I'll just go ahead and show you the pictures here. So draw these down on your guided notes. All right, we've got some guided notes for you. Can happen two ways. So if we have a chord that looks just a generic chord here, AB, it's going to divide this circle. It's going to split it up into two arcs, a minor arc and a major arc. So minor arc AB and major arc ACB. Remember, with minor arcs you label them with 2 letters. With major arcs you label with 3 letters. That's why we needed this little point C down here. So that's one way that you can have a chord divide up the arcs of a circle. Okay. The other way is if you have this special type of chord, which we call the diameter. If it goes through the center, then this chord right here would divide this circle into 2 semicircles. All right, so these are the 2 different ways. So you can either have a chord divide a circle into a minor arc and a major arc, or you can divide a circle into semicircle and semicircle. Okay? So that's the only way that could happen with just one chord. So like I said, we're going to talk about a lot of theorems today. I think we've got 4 theorems. So let's go ahead and get started. The first fact/theorem you need to know, and we're not going to prove it. Remember, theorem is something you can prove. We're not going to prove it. We're just going to accept it to be true and kind of move on. So let's look at this first one here. It doesn't have a name, so you don't have to worry about memorizing a name of this theorem. What it says is, in the same circle or congruent circles, 2 minor arcs are congruent if and only if their corresponding chords are congruent. So fill in the blanks there on your guided notes, and I'm going to scroll down. If you need to go back, just let my substitute know. So here we go. So here's a picture of it. Almost looks like a baseball. We got those 2 chords there. So what we're saying here, and I would make this note on your guided notes as well. So draw this and make that note down there. But it says, well, it gives us that we have congruent chords. So if we know we've got congruent chords here, what we can say is that these arcs, and I'm going to highlight these, so these 2 chords, the arcs that they intercept are going to be this arc, and let me do this in green, that arc, and that arc. So what we're saying here is if we have these 2 chords congruent, those 2 arcs have to be congruent. And vice versa. If we knew those arcs were congruent, then we know the chords were congruent. All right, so hopefully that makes sense. Now I'm going to try to explain why that's true. And again, we're not going to prove it. I'm just going to try to illustrate it for you. So let's say I didn't have congruent chords. Let's say I moved CD and made it bigger. So in order to make it bigger, I still want to make it a chord, so I still have to have endpoints on the circle. But if you notice, what's going to happen to the arc? Let me move D down here. Sorry, wrong one. Still the wrong one. Move D down there. So if I made that, now that would not be congruent. So hopefully you guys noticed I made that bigger. All right, this chord is no longer the same length as AB. Okay, CD is no longer the same length. So when I did that, the arc became bigger. All right, we made the arc bigger that it intercepts. All right, so therefore the arcs would no longer be congruent. Now if I put it back, undo this, Now we have congruent chords again, and now we have congruent arcs as well. All right, so hopefully that allows you to visualize what's going on here, why this theorem is true. Again, we're not going to go through the proof. Just want to accept that and move on. All right, let's keep going. So let's do an example. Now this one should be easy. Again, I've got it written down for you. Just draw the picture. That's all you got to do. And solve it. So now would be a good time. I'm going to scroll down so you can see the picture. Let me read it real quick though. So it says, in the diagram, circle P is congruent to circle Q. And this is something I don't think I mentioned in the last video. So let me go over this here. This symbol is the symbol for circle. Alright, so it's just a circle with a dot in the middle. That's how we symbolize a circle. And by the way, we always label circles by their centers. Okay, so whatever the center is, that's how we know which circle we're talking about. So this one's circle P, this one is circle Q. Alright, so we know the circles are congruent. We know these chords are congruent. FG is congruent to JK. And we also know that arc JK is going to equal 80, and I've got it written down here. So we want to find the measure of arc FG. So guys, go ahead and do that. There's not a whole lot of work required, but go ahead and figure that out. You can pause this and see if you can figure it out. Alright, I'm going to go ahead and I'm going to talk about it. So we just said the circles are congruent. Now I know the circles are congruent here because the radii are congruent. That's a radius, that's a radius. If the radius is congruent, if the radii are congruent, the circles have to be congruent. Right? They've got to be the same size. They're going to be the same size, same shape. Obviously circles are always the same shape. So, what else? Yeah, we got chords. These two chords are congruent. So if we have congruent circles and congruent chords, the fact that we just talked about, the theorem that we just wrote down, is that the arcs are going to have to be congruent as well. Alright, so if this guy's 80, this arc that this chord intercepts, which is FG, is going to be 80 degrees. And we're done. Alright, so that one's just basically asking you, do you know the theorem that we wrote down on the slide previous? Okay, let's move on. So that's all you've got to do for this guy. Moving on. Here we go. Next theorem. Make sure you fill in the blanks here. I'll try to give you an illustration as to why it's true. If one chord is a perpendicular bisector of another chord, then the first chord is a diameter. It has to be a diameter. Alright, so let me show you the picture here. I'm going to make a claim after I show you this picture. So draw this as well. Drew a circle, and we've got one chord. Hopefully you notice that SQ, if you look at how we mark this, SQ is going to be perpendicular to TR, and it's also bisecting TR. Okay, we're saying TP and PR are going to be congruent. So this is a perpendicular bisector. Alright, so what we're allowed to claim here, so what this theorem tells us we're allowed to say is that this first chord, SQ, has to be a diameter. Alright, and I'll try to explain why that is. Again, I'll move stuff around here in a second, but this is the claim that we're allowed to make now that we know this chord is a perpendicular bisector to the other chord. Alright, so let's try to understand that. Let's try to figure out why that is. Again, we're not going to prove it, but I'll just show you an illustration. So let's say this looks like it's a diameter right now. Let's make it more obvious that it's not a diameter. So let's say I move this up. Move that in a little bit. Is that going to be a perpendicular bisector anymore? Well, it still might be perpendicular, but hopefully you guys can tell it's definitely not a bisector anymore. Okay? So that's why, obviously, SQ is not a diameter in this case, and it's obviously not a perpendicular bisector either. It might be perpendicular, but it's not a bisector. Right, so that's the idea. That's the reason, that's a way to think about this. It's a way to remember that this fact is true. Alright? So that's all there is to that theorem. Now moving on, the next theorem is going to be very similar. It's almost the converse of this theorem. Okay, now remember, converse is just writing the statement backwards, changing the hypothesis and the conclusion. All right, so we're saying the converse, well, essentially the converse is true. So let me go ahead and write down this theorem. I'm going to show you this theorem at least. You guys write it down. So if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. Pretty much the converse of what we just said. So here we go. Let me draw another picture. You guys do the same. Again, if you need to pause, if I'm going too fast, just let my substitute know. So there's the picture. All right, let me talk about this. So what we're saying here, here's the given information. So I haven't written this down, but EG is a diameter. Okay, so that'll be the center of this circle. You can label it if you want. You can call it circle A or whatever. But we've got that center of the circle. And we know EG is a diameter now, and so we also know that it's perpendicular to this chord. So what this theorem is telling us is if we have a diameter that's perpendicular to a chord, then what can we say is happening? What does the diameter do to the chord? Well, it's going to bisect it. All right? So therefore we know this has to be congruent to this. So let me just scroll down. So therefore we know EG bisects segment FD. It's also going to it's also going to bisect the arc as well. All right. So what we also know is that arc FG is going to be congruent to arc DG. I guess that's another claim we can make. Yeah, you can say both of those things. So it bisects the chord and its arc. And you might be asking, you can write this down if you want, you might be asking, is it going to bisect that major arc as well? The answer is yes. It is going to bisect that also. So you could say this arc right here, FE, is going to be congruent to ED also. Okay, so that might be another claim we can make. Okay, so that's that theorem. So let's move on. I think I've got an example here. Yeah, I've got this example. So you guys try this one. Pause it if you need to. And I'm gonna answer this real quick. All right, so to answer this guy, it says use the diagram of circle E to find the length of segment AC. So here we go. First of all, I know BD is what type of chord, what type of segment. It's going to be a diameter because it goes through the center. Right? Hopefully that was clear. So we know this is a diameter, and we know it's perpendicular to a chord. So let me go back to that last theorem. It says if a diameter of a circle is perpendicular to a chord, then the diameter is going to bisect the chord and its arc. All right, well that makes this very easy then. Again, let me say this again. We've got a diameter here, and it's perpendicular to this chord AC. So that means it's going to bisect that chord. So if this guy's 7, bisect means cut into 2 equal parts. This guy would have to be 7. Done, answer. Circle it. That's it. Okay. There we go with that one. Moving on. Yeah, guys, I'm moving fast. I don't want these videos to be so daggone long. They take all class period. Now, if you guys need to slow it down, by all means, do so. Here we go. Next theorem. I believe this is the last theorem on your guide notes. Let me double check that real quick. Yep, the last theorem. So in the same circle, or in congruent circles, 2 chords are congruent if and only if they are equidistant from the center. All right, so this is a good one. I'm going to get rid of this shade here. Well, cat's out of the bag there now. So here we go. What we're saying with this, I've drawn a picture. We're saying if these two chords are congruent, so if CD is congruent to AB, maybe I should read this a different way. Instead of saying that, I should say CD is congruent to AB if and only if. Remember, IFF means if and only if. GE is equal to FE. So what we're saying here, these two chords are congruent if and only if they're equidistant from the center. All right, so we're saying in this case E is the center of our circle. So if these two chords are equidistant from that, they are going to be congruent. Now let me explain why this is true. Again, not going to prove it, I'm just going to illustrate it for you. So what if I wanted to move this closer? Let's just pick one of these chords and move it closer to the center. So here goes. Now, if I move it closer, if you guys notice that, hopefully you can see this on the camera, that's no longer a chord, is it? Because its endpoints aren't on the circle. So I'm still going to need that to be a chord, but what I'm going to have to do is make it bigger. I just made that chord bigger. All right, so therefore, if I move it closer, they're no longer equidistant, and therefore the chords cannot be congruent. All right, because I just had to make the one bigger. All right, I could do the same thing going further away from it. So if I made this chord further away, I have to make that smaller. So hopefully you guys can tell now that obviously those two chords are not going to be the same length anymore. So in order for chords to be the same length, they have to be equidistant from the center. So hopefully that is clear. And one more thing to mention, guys, we've talked about distance, haven't we? The distance of from a point to a line. Remember, the distance from a point to a line, you always have to draw perpendicular segments. That's why I drew perpendicular segments here. All right. So that's going to represent the distance from a point to a line. So guys, this fact we can deduce from this information right here, based off that theorem. All right, so one more example to get through. I'll walk you through it, and then we'll call this lesson finished. So here we go. So I've got this written down for you. You need to draw the picture on your guided notes. I've got all the information you need on the guided notes here. It says, in the diagram of circle C, here, let me go back up just to read it here. In the diagram of circle C, QR is equal to ST, which is equal to 16. So they're equal to each other and they're both equal to 16. Find the distance from C to QR. Alright guys, so hopefully you can see which theorem we're going to use. It's the one we just talked about. The one where we talk about distance from, if chords are equidistant from the center. Okay, so that's what we're going to use here. So here's the picture. Let you guys draw it. And you guys solve it without me here. Pause the video so you can have time to solve it. Okay, I'm going to talk about it now. So we know these chords are equidistant from the center. My bad, I just gave it away. Sorry, that's not what we're given. I apologize. What we were given is that the chords are congruent. Okay, so we're given congruent chords. So if we're given congruent chords, two chords are congruent if and only if they're equidistant from the center. So since the chords are congruent, I can say that the chords are equidistant. So what does equidistant mean? Well, hopefully everybody knows what that means. Equal, distant, distance. So their distance is equal. So the equation I need to set up to solve for x is, and I do need to set up an equation. I need to figure out what x is before I can figure out any lengths. So the equation I'm going to set up is 2x is equal to 5x minus 9. Alright, the reason, again, I just want to explain this a little bit further. So the reason why I set those equal is because if the chords are congruent, they have to be equidistant from the center. Alright, these represent the distances from the center. Alright, so I know those two have to be equal. So all I got to do is solve that. I don't know, whatever you want to do first here. I'm going to subtract 5x from both sides. So 5x minus 5x is 0. 2x minus 5x is negative 3x. Don't forget the negative. That's equal to negative 9. And then to solve, I need to get x by itself. I need to isolate x. So in order to undo multiplication by -3, we divide by -3. And so x is going to equal -9 divided by -3. It's going to be +3. Now, did we answer the question? Always look back and see if we answered the question. We found x. Does it say find x? Nope. It says find the distance from C to segment QR. Well, the distance from C to segment QR is that length right there. Well, we found x, so to find that distance, it's going to be 2 times x, which, well, 2 times 3, which is 6. So I guess we can say that's 6, circle it, that's our answer. And guys, that'll wrap up this lesson. I'm sure I'll have an assignment for you guys to do. But yeah, use this to figure out how to work through that assignment. Okay? All right, that's all I got for you guys. Thanks.